I know that Maxar has never presented at EnerGIS. I don't know that we've even been at an EnerGIS conference before, so I think this is a first for us. And I will preface this to say that my presentation is very different than the others that you've seen. I'm not a GIS person. Maxar is not a GIS shop, though we do use GIS software for a lot of individual uses to manage our data, to manage but we're not a GIS shop. So we were asked to give a talk on what happens after you launch a satellite into outer space. You hear about it, you hear about launches all the time, and then some months later you might have data at your fingertips. But what happens in those weeks and months between launch and data being delivered to our customers? Of course. First, I do want to introduce our constellation. So at Maxar, we operate the world's most advanced Earth imaging satellites. So we have 4 legacy satellites on orbit now. These are the first 4 that you see, Worldview 1 through Worldview 3. In recent months, we launched 4 additional next generation satellites, we call them, and in about 2 to 3 more months, we're going to be launching 2 more satellites. So with our existing constellation, with the 4 satellites there, we collect roughly 4 million square kilometers of imagery every day, which amounts to about 1.4 billion square kilometers of imagery every year. With the addition of these 6 new satellites that are about to be online, we're going to up our intake to roughly, something over 6 million square kilometers every day. And this whole constellation will allow us to revisit pretty much any point on Earth 15 times a day. And that's pretty new. For Maxar, certainly, and new in the EO Earth observation industry. So just introduce some of our products a little bit. Certainly the bread and butter of Maxar are our 2D core imagery, is what we refer to it. It's the pictures that we take from outer space. 2 of our satellites on orbit now collected about 50 centimeter GSD resolution. The remainder, we have one that collects at 40 centimeter, and the remainder all collect at 30 centimeter class imagery. Most of them are loaded up with, we collect panchromatic data, but certainly we also collect data in the visible, near infrared, and shortwave infrared. Using this 2D data, we now have quite a library going of 3D information products. So these are DTMs, DSMs, digital surface maps, and other 3D vectors. As well as looking down at the Earth, we can also point our satellites up and out, so we can collect imagery of other space assets. So in this picture is the International Space Station. This was acquired earlier this summer. This is also a new offering for Maxar commercially. We've been doing, satellites have always had the capability of doing this, but to offer it commercially, we've been doing this for about a year. So that's actually where I do a lot of my work lately, working with customers who need pictures of their own space assets. Just to round out some of the other products that we offer, information layers, under this umbrella portfolio that we call Access, our data is available to our end users in a subscription form. So for subscription platforms, we have a nice, easy-to-use UI where users, it looks a lot like any old GIS interface that you might encounter. But also the data is available through APIs. And then finally, we have a lot of analytics that we offer that are built in shop. So change monitoring, and thematic layers. So aside from the formal products that we offer at Maxar, there's a good chance that a lot of you may have encountered our data just on a daily basis. So if you use map apps like Google Maps or Apple Maps, if you look at the satellite imagery, that's often our data. Sometimes it's coupled with aerial. Or there's a really good chance that you would have seen our imagery on the nightly news. We have partnerships with Reuters, with AP News, with BBC. So unfortunately, it seems like it always happens with or if our imagery is exposed, when something bad happens in the world. We have wars in Ukraine, we have wars in different parts of the Middle East, or natural disasters. So when you see the news, or you open up your paper and you see a satellite image, it's probably our data. Or, as GIS professionals, you may have encountered our imagery just in your own projects. We do have partnerships with some big GIS software companies that have been talked about today. They buy some of our, we call them base maps, or our vivid suites, or mosaics. So, even just using as a background in your projects, there's a good chance you're using our data. Okay, so now we're going to move on to the main theme of the presentation. Now that I've introduced the constellation, I'm going to talk about what happens after we launch. And I have a video at the very end that shows the rocket launching, our satellites being deployed, and some cool things that we can do with those satellites. So specifically, I'm talking about from this point on, add maybe 2 or 3 months to this. So this is actually our Legion being launched. This was back in May. So this is the moment that the satellite detaches from a dispenser, and it's just floating out there. So the satellites and the spacecraft separate, and it's just sort of hanging out for a few minutes. So what happens is a pretty standard set of procedures in these industry known stages. So pretty much every satellite would go through most of all of these phases or stages, as we call them. And I'm going to talk about each one of these a little bit more, but the first stage is called LEOP, launch and early orbit stage. Then we would move into commissioning, then onto validation and calibration. That's the one that can be iffy. Not all satellites need to go through validation and calibration. We do. And then we have our initial operating capability, and then we're fully operational capable. I'm going to talk about each one. So, LEOP. So the goal in LEOP is to turn the thing on. We're going to turn it on, make sure it's healthy, that we can communicate with it, and that's kind of all we do in that stage. We want to make sure we preserve the life of it. This stage can last a couple of days, a couple of weeks. It just depends on the complexity of the vehicle itself and all the onboard subsystems. The first thing that would generally happen in those few moments that we're separating from the spacecraft, we're going to unfurl the solar panel. So on this is an artist rendering of our Legion, or Worldview Legion satellite. That flat piece that's facing away, that's actually a solar panel on the other side. So that thing would unfold, and then there's probably other hardware that deploys, usually antennas, so that we can communicate with it. So it's powered, we can talk to it a little bit, and then the next thing that happens, and this can take again a few days, a few months, or well, a few weeks, it's going to eventually land in its final design orbit. So reach that orbit, and then it's going to be relatively stable in that orbit. And at that point, we move into the commissioning phase. So in commissioning, the goal here really is to establish our baseline performance of the instrument and subsystems. And as always, we need to preserve and ensure the safety of the vehicle. These are very, very expensive assets. So we take a lot of care after they're launched into space. So we may do things like refine our software, upload software packets for things like collision avoidance. There are a lot of pieces, parts just floating around there in space, and we need to make sure that we can avoid them because we don't want to crash into them, breaking some expensive piece of equipment. We go through maneuvers like avoiding the sun. It's very, very bad for an EO type, specifically an EO type of imaging satellite to look directly at the sun. It'll fry the focal plane. Same is true for some ground targets. There are some ground targets that can fry a focal plane. So we need to ensure we have software in there that automate us from pointing directly at any of these very dangerous targets. We're also continuing to refine the attitude and orientation of the spacecraft if we need to, and we always need to. But finally, I suppose the last thing that's really happening here, we're really starting to test the transmission, the data links with our ground stations, so the uplinks and the downlinks. Initially, in layout, we may just send little bits of commands, turn on, turn right. But through commissioning, we're uploading more intense data packets, again, for uplink and downlink. Next, and commissioning can last weeks to months. Again, this all depends on the complexity of the satellite instrument and subsystems. Once we have a baseline performance and we're pretty happy with the way things are moving on, then we would move into a phase that's called validation and calibration. So here, the goal here really is to fine-tune all of our onboard systems. And for us, we have very, very expensive and exquisite scanners on board that we can take high-resolution imagery for our customers. This takes some time. We're cross-checking. Basically what we're doing is we're cross-checking the data that's collected from the satellite with targets on the ground of some known value. So it's this cross-check of data, and then we start to make any kind of corrections to systematic problems that we may see. I'm actually going to come back and spend some more time later in this deck on BNC, so we're going to put a pin here. But to round out these 5 stages are, what we call IOC and FOC. Once we have some baseline performance established and we're happy with that, then we would think about IOC. And this is really different for different vendors, satellite providers. It's basically, we're able to provide the minimum amount of data to a minimum number of customers. So we've just taken the training wheels off the bike. We're pretty sure we're not going to fall over. We might be taking the bike around, the driveway for a spin for a few weeks before we're comfortable going around the block and in the parking lot, etc. So we gradually ease into FOC, and then we're in FOC for the life of the program. Okay, so I keep saying we're going to come back to B and C, and we will. But to understand what we're measuring in B and C validation and calibration, we have to know what we're measuring against and why. So this goes back, I'm just going to talk very briefly about design specifications. What is it that we're validating? How do we know what to even look for? So some years prior to a highly exquisite satellite being launched, sometimes going back years, we get a bunch of smart people in the room. These people are engineers, they're CEOs, they're stakeholders, investors, certainly they're customers, and they all have ideas about what it is that they want to see in space in 3, 5, 10 years' time. So we have the ideas, the ideas are endless and boundless, but we also have to have an eye toward, the macro technical environment. So these people, while they may have all the ideas in the world, we want to take advantage of new emerging technologies. So, we're building for machine learning and AI and not for like abacus and DOS days. So we need to have a look to the future. Of course, there's a budget constraint, all of the good ideas in the world. If we have investors, we can only get so much capital to invest. Anyways, this kind of will all dictate the design requirements. What is it that the satellite is supposed to be doing from space? So this slide just lists some design specifications that we have for some of our satellites. So these, in reality, this list is hundreds of lines long. But I'm just going to dig into, double-click here on a couple that probably our customers experience most readily. And that would be imagery resolution, accuracy, and revisit. So, GSD. So, like I mentioned, 2 of our satellites on orbit now collect at 50 centimeter GSD, which is great and lovely and perfectly suitable for many, many use cases out there. However, with our newer satellites, and that actually includes WorldView 3, which has been on orbit for 8 or 9 years now, we had a hard requirement that our next generation satellites must be 30 centimeter class imagers. So, this is what our customers expect from us. It best suits their use cases. The better the GSD, the more detail can be discerned from an image. And I think this slide kind of showcases this, right? So as you move from left to right, you can start to see more and more clearly as the GSD or resolution improves. Certainly on the left, I can see that there are airplanes. I can see that there are individual airplanes. But as I start to move right, and I'm starting to see what 30 centimeter data looks like, I can now probably really start to tell the difference between these different types of aircraft. Maybe I can see if they're weaponized or not. I might be able to see if there are any kind of markings on the side. I can see, who runs that or operates a specific airplane. I think this showcases the importance of GSD. So the next thing that we have a very, very hard requirement for is geolocation accuracy. And this is basically to ensure the most reliable positional accuracy of our imagery, which I think everybody here as GIS professionals can probably appreciate. Anybody knows where this is? Geolocation accuracy. This is an image courtesy of WorldView 3. But yeah, we're here. So, even if we're offset by tens or 100 meters, our map app or our Google Drive or whatever could potentially get us to the wrong building. We don't want that to happen. Okay, so the next concept, I need to refer to my notes here because this is a little bit more complex, but we have a requirement for our next-gen satellites to be able to collect multiple revisits per day by leveraging the whole constellation. So, let me see my maps here. Okay, good, that's playing. Many EO satellites are launched into some sort of a polar orbit. So what does that mean? A polar orbit means that a satellite will revisit the North and South Pole in a LEO, low Earth observation orbit, roughly every 90 minutes. We, Maxar and many satellites actually, are in a sun-synchronous type of polar orbit. This actually means that our satellites cross over the equator at roughly the same time every day, solar noon. There are a lot of pros to this, mostly pros to this, mainly with lighting conditions. When the sun is behind you, and you're taking a picture of something, it provides the best illumination conditions. And it's true if you have your cell phone and you're taking a picture of your cute little puppy, it's better if the sun's behind you, and then you can get the best possible picture. The other thing that it's really great about is, well, if you're passing over the target at the same time every day, I can start to establish a pattern of life scenario. So, if I care about how many cars are in the parking lot of Walmart, and now all of a sudden I'm noticing on Thursdays at 12 o'clock, there's always more cars, and on Mondays at 12 o'clock, I start to make do some sort of analysis on that. But if I care about what's happening in the Walmart parking lot at 3 p.m. or 7 p.m. or 6 a.m., I'm kind of out of luck because my satellites don't pass over at those times because I'm in a sun-synchronous orbit. So what do? We're launching 4 of our new Legions into a different orbit or ground track. And this is called a mid-inclined orbit. So instead of passing over the poles, we're now passing over about 45 degrees from north. It just so happens that at these latitudes are where most of the Earth's land is. Therefore, that's where most of the humans are and where most of anything interesting happens. So now we can get up to 15 collects per day. So we have satellites that are going in a sun-synchronous orbit and other satellites that are going in an inclined orbit. Oh, okay. Now we can go back to D&Z finally. So back to present day. So remember, VNC, the point of VNC is that we are fine-tuning our satellites, and we need to ensure repeatability of the performance of the onboard sensors, which is super important to us. Two big focus areas during VNC are specifically called geometric calibration and radiometric calibration. Geometric calibration, locational accuracy; radiometric calibration, and broadly speaking, has to do with image clarity. In reality, we conduct VNC throughout the life of the program, so we go out multiple months per year for 10 years, and we're constantly taking measurements to make sure that we understand the performance of our onboard sensors. So geometric calibration is to ensure that the spatial information captured by the scanner corresponds to real-world coordinates. And there are two sort of things that have to be done here. One is we have to understand our external positional accuracy of the satellite, and we also have to understand the internal relative accuracy of the instruments. So external accuracy. Our satellites are in space. We need to make sure that we can point those things down or out, but down for Earth observation. And we're not in space. There's not a lot of leeway here. So, whoops. So we implement these little instruments that are mounted on the outside of satellites, and they're called star trackers. So star trackers help us align our gyroscope or reaction wheel. It's the thing that makes the satellite move to the telescope. So stars are fixed features against the blackness of space, and we leverage preloaded star catalogs to identify star patterns and then align and orient the satellites accordingly. And a fun fact that with these star trackers, we can align our satellites to within 60 millionths of a degree of error. So they're highly, highly accurate with pointing accuracy. So now that we know that we can point the thing, either up or down, wherever we decide, now we have to work on correcting for any sort of distortion that might be in the telescope optics or the focal plane. So one way to do this is to take images of things of known precise geolocation. So it could be as obvious as this. I have a piece of land, I'm going to throw out some panels. Those panels are GPSed into place. I take a picture from space, and I can start to correlate and hone in on any kind of systematic errors that might be present in my data. The next consideration is the spectral accuracy of our products. So radiometric calibration, this ensures that a sensor's recorded digital number, or the pixel, if you zoom really far in on an image, you're going to see the actual pixels, so that those pixels accurately reflect true radiance values. So, for example, we have some of our satellites collect multispectral data. We have a little detector. Each one is about the size of my pinky. So for the detector that would detect the blue band, for example, which might have a wavelength of about 500 nanometers-ish, that's what it's supposed to be when we measured it in the lab. What you're going to see in a few minutes, the ride up to space is a rough one. Things can jostle. And also sensors can degrade over time. So we need to ensure where our band centers are over the life of a satellite. So we take all of these measurements to do that. How do we do that? In some cases, we have these giant panels. They're calibrated. They're very, very heavy. They're very, very expensive. And we roll them out, and then we take a whole bunch of pictures with them of them from space. These panels are measured in a lab, and they have a known reflectance, radiance emitted value. So then we can take hand measurements of the spectrum that's reflected off of those panels, and then we can do our cross checks. And just a fun fact, that's actually me, like 20 years ago, with the backpack on. And at my feet, you don't see in the picture, is a panel that I'm taking some measurements of. But back in those days, spectrometers were big and you had to wear them on your back. So we do this, again, we'll do this hundreds of times, probably thousands of times throughout the life of a satellite. But we don't have the luxury of being able to afford all of these giant panels and deploying them all over the world in all sorts of weather conditions. So we take advantage of materials of known spectral reflectance. There are spectral libraries out there all over the place. Somebody this morning was talking about national labs. National labs have their own spectral libraries that are out there for the public. Stanford has them. This information is pretty well publicized. But we just point the satellite at things of known, ground features of known spectra. So sandy soils, or snow, open water, forested areas, features of known man-made materials like concrete or cement, or back to these fun little panels. They're actually called MTF, modulation transfer panels. They're very, very handy for geolocation. You can tell exactly where, you know, the four checks meet, the black and the white checks meet. I can tell you exactly where that is on the face of the Earth with GPS. But they're also wonderful for determining what levels of signal to noise might be in your data. And once you know that, you can start to address any sort of sharpness or crispness of the imagery. And then finally, for radiometric calibration, if we know the true radiance values captured in our digital counts or in our pixels, this can allow our users to do fun, creative things like generate LC maps or to perform some sort of material identification on imagery where you can do some spectral matching. So that's my last slide, and I'm going to end this 2 minutes to spare with a video, and I'm hoping that the sound comes through. This is literally called our hype video. It's very hypey, so brace yourselves. I hope